All right, I'm back here with you, Mr. Fugay here. We're going to finish up the final example from the part 1 video. Ran out of time, 15 minutes early. Allotted time we're allowed on Screencast-O-Matic, so had to record a second clip here for you for the last example. But I want to go back to this because this is how we started the first video when we talked about the ladder problem, and here it is. So remember that we're looking at this. The relationship that we need to find here, every relationship we've done in this video so far has either been some sort of area, volume, or surface area. But we're not really looking at analyzing any of those metrics in this question. In fact, the only metrics I care about are the height, this x value here, and then this 13 is a constant, but it's definitely involved in this. At any given moment, this ladder is making a right triangle with the ground and with the wall. And so the lengths of these three sides can be easily related to one another that we can use the Pythagorean theorem. And that's the relationship we're going to be looking at here in this question. So again, just to put a visual on our drawing here, okay? We have this ladder here, and it's really important to note that this ladder is going to remain 13 feet no matter where it's at along the way. And we can use that link to help establish that. We have this x and we have this h. Now what's known here, let's read through the rest of this. The bottom of the ladder slides away from the wall at a rate of 2 feet per second. So there's that word rate again, and it's sliding away from the wall. So that's going to actually tell me that that's the value or the rate of the x changing. So it's going to be dx dt. Now the x is getting larger as the ladder moved away. So as the ladder gets further and further away, it's the foot of it that is, dx dt is going to be a positive 2. Now this should give us a preview because what we're actually going to do here is how fast is the top of the ladder or the height of the ladder going to change. So that's going to be this here. Now quick prediction, would this answer be a positive or a negative rate? Since the height is getting smaller as the ladder is getting pulled away, I would assume that this dH dt should be negative. This is going to be a good error analysis thing for you to check out. That if you get a negative answer for dH dt, then we know that we've probably done this correctly. All right. And the last information that they gave us here is that the base of the ladder is 5 feet from the wall. So that's just going to be the x value. All right. So let's go ahead and let's look at our Pythagorean theorem. So it's going to be x squared plus y squared equals, now I normally would write z squared, or actually let's use h because we used h here for the other side. Sorry. X squared plus h squared equals, now normally you would write in like z squared or c squared, but I want you to remember that this 13 is a constant. It's a constant, and we love constants because that's one less thing I got to take the derivative of. So that's just going to be equal to 13 squared. So keep in mind, if it doesn't change over the course of time, that is a constant. If you're looking at a snapshot and then you're looking at x is 5 is a snapshot value, not a constant value. So those are kind of the difference you need to look at here, right? We're looking at a still image where x is 5, but as soon as I hit the play button, that 5 is going to change, 13's not. Let's go ahead and take the derivative of this. So it's going to be 2x dx dt plus 2h dh dt. This is not 2 times 13, no power rule here, right? The derivative of a constant is 0. So there is our derivative. Now let's go ahead and let's plug in what we know. We know 2 is our value for, 5 is our value of x, 2 is our value for dx dt, my apologies. 2, now we actually don't know what h is, and we also don't know what dH dt is. So we've run into a crossroads. We've run into a problem, okay? And what we have to try to figure out now is what are we going to do to solve this problem? Because I have 2 unknowns. And here's the thing about related rates. Related rates can have as many rates and as many values as we want, as long as we only have 1 unknown. And we have 2 unknowns right now. So a little pause here for you to think about, what can I do to figure out what h is? To find h, we're going to do what we've done since we learned Pythagorean theorem years ago in middle school or in geometry, and that is we can actually just solve the Pythagorean theorem by saying 5 squared, which is x, plus h squared equals 13 squared. We're solving for the snapshot, for this moment of time where x is 5 and the ladder is 13. So we're going to end up with h squared equals, so 25 from 169 is 144, so h is going to be 12. So we actually now know this new value of 12, this new snapshot value that I can plug in for h. Now we have our unknown, which is dH dt, and that was the thing we wanted to know, right? Or we want to find and we want to know is missing. So 5 times 2 is 10, that's 20. 24 dHdt. And so when I end up solving this, I'll just kind of fast forward. We'll subtract 20, divide by 24. So the answer is negative 20 over 24, or better known as negative 5.6. Again, height is in feet, time is in seconds. So this is going to be feet per second. And oh, by the way, we've confirmed that negative answer we talked about earlier. It is a negative answer. And so there is an example using the Pythagorean theorem and relating their rates to one another. Again, when you get stuck with these questions, I want you to go back and fall back to what I shared in the very beginning of the video, and that's this 5-step process. This is going to be a good logical progression that you want to work yourself through, no matter how easy or difficult these problems get throughout the 3-part series here that we're going to be doing. Okay? Once again, thank you guys for watching, and good luck in practicing this.